Thank you very much. Good evening to all. It's a great pleasure to be here after more than 20 years and to see how much the center has evolved, how important this center has been for Latin America and particularly for the Amazon. A lot of inspirational research for the Amazon has been carried out here over many decades. So I have a great respect for the center, for the people who make this center. It was also a great pleasure to meet many of my friends here, friends who I've been in contact with for some people 30 years. I'm older actually than most people here. So again, thank you very much. When you talk about the focus of this project center, tropical conservation development, my approach today is talking about risks. If you talk about development, of course, development is very closely associated today, modern world, with capitalism. And capitalism really tried to quantify risks. Conservation, I'm not sure. I'm not a conservation biologist. I'm not sure how conservationists consider risk. But anyway, I will try to show you, to tell you a little bit on some work, part of my work of my former students, and part is just a review of some important results, to quantify the risk that we face if we continue changing the global climate, if we continue deforestation, and also if we continue using fire in tropical and subtropical agriculture the way we are doing. This is something that really concerns me more and more. I don't know if you've seen the data. The data shows September was the month, 20-year record breaking in number of hotspots. So we are not progressing much in terms of controlling fire, at least in Brazil, but I think it's all over the Amazon. So I'm trying to look at those things, quantify those elements. Because, Abisita mentioned you're all converted, so I'm not going to spend a lot of time in introductory issues because you know everything about the Amazon very much. Can I have the lights off?
Yeah, turn off those.
Okay, thank you. Okay, I acknowledge all these people who helped me, my students particularly, for a long time. So I will basically focus on this item, then I will conclude the second item there, which is trying to quantify risks of land use and climate change. But let me just start just to make this overall remark. You're very familiar with this issue. The Amazon is a regional entity of the Earth system. It's a very important entity. We are in the Anthropocene, and basically we try to quantify what the risks are for this important system, and particularly considering the great acceleration which marks this Anthropocene epoch. This data is certainly very well known to you. It's very unique, it's powerful regional entity of the Earth system in all these aspects. Global carbon cycle is a big sink. The forests, the undisturbed forests are a big sink, although it's very hard even to qualify what is undisturbed. But anyway, the forest away from biomass burning is important sink, powerful hydrology. Of course, perhaps even 10% of species, over 1.2, 1.3 million species in the Amazon. It's an important climate stabilization because it's an important heat source for the atmosphere. And of course, not least important for keeping cultural, ethnic, linguistic diversity. So, however, the great acceleration did not leave Amazon out, although in the world as a whole, it started after World War II. In the Amazon, as you all know, started with most Amazonian countries decided to integrate economically the forest in the 70s. Starting in the 70s, you see all these indicators go up pretty much almost exponentially. And this is really what we are concerned about. So let me then move to the main part of this talk, which is quantifying these risks. I started working almost in 1988 with Pierre Sellers, a former astronaut who died last year, and Jagadish Shukla in Maryland, University of Maryland. So we quantify and we came up with this savannization hypothesis. If we deforest all of the Amazon, all those points marked as the Amazon, and then a post-deforestation climate would not have forest in these points marked as 6. The new climate will be a savanna climate. So that we came with this so-called savannization hypothesis, which was in fact a climate change, regional climate change hypothesis. It was not ecological hypothesis in the sense of ecological succession, very complex issue, ecological succession. We know much more than when we were doing these studies in the late 80s. But anyway, this became an issue of interest to many people. And of course, there is many groups who are working for decades on issues, quantifying these risks. I show this NASA image of greenness just to, it's also very pedagogical because you see a lot of seasonality in the savannas, but then you see that dark green. So the Amazon, of course, is well known, very aseasonal. So that's a very important element of climate-forest interactions, very aseasonal. And why is that aseasonal? And we have here rainfall. And I'm going to talk about, it's very important to understand what drives the boundaries between savanna and tropical savanna and the Amazon in that elongated northeast southwest shape. And it has to do with the number of dry season length, the dry season length. And you see here, it's dry season length, longer dry season savanna, short dry season forest. And this is a very abrupt change. And this is really a very important, I don't have time to tell you all that we know about that, but I just want to show you that this region, and I will pay a lot of attention to this region, northeast, southeast and northeast Amazon, because it has a lot to do with the risks that the Amazon. So that area has also long dry season, that yellow there, 3 months dry season. That area as well has a very almost savanna-like climate envelope. So longer dry season and warmer as well. So this is an area that even without any modeling, you might expect the risks for changing vegetations or savannization would be higher. Also, this graph from LBA results show another important element. The color lines are evaporation from forests. You see very little seasonality. And for savannas, it's very profound seasonality. Savannas are not evapotranspiring much in the dry season. And this has to do with this root dynamics, specialization of tropical trees, that they draw water in the wet season up to 3 meters, but in the dry season, they draw water up to 84. So it's an adaptation, and these deep root trees are very common in that area that I show, southeast, northeast, let's say around Santarém area. Those trees are very prevailing in that area. And this is an ecological adaptation for a longer dry season. Okay, with a student of Marcos Oyama, we found out that the Amazon may have 2 stable climate biosphere equilibrium. One is the top one that you see, it's pretty much the equilibrium today. These type of models, you just put climate data and then you predict what the equilibrium vegetation will be. So the vegetation is not there. It's just the result of this modeling. And the bottom one is another one that we found out is stable, statistically robust, and you see much more savannas, the pink color in that area, Eastern Amazon, Southeastern Amazon. So this led us to think what would really drive a change between the top one and the bottom one. Schematically, this is what we mean. One equilibrium on the left diagram, which is the current one, forests in most of the Amazon, and another equilibrium, second state stable, which is forests in the west, savannas in the east, and the right hand diagram shows what droughts and the fires will do to make the second equilibrium much more robust. It will be very difficult to change. So why is that so? Let me show you this complicated diagram. I could spend half an hour explaining all the dynamics of rainfall mechanisms, rainfall producing mechanisms in the Amazon, but let me simplify. I just want to pay, those are the four main rainfall mechanisms in the Amazon. Very close to the Andes is that concave shape of the Andes, 3, 4, 5 meters of rain. And then you have this South American monsoon system zone that we call South Atlantic Convergence Zone, also a lot of rain. Then near the coast, it's mostly forced by sea breezes. And then you have that area that I call instability lines. That's the area where rainfall is less, longer dry season. Instability lines are atmospheric perturbations, gravity waves originating from the sea breeze, and they sometimes get all the way to Iquitos, and they cause rainfall, but they are rare. So most of the rainfall you see here on this upper diagram in blue, these are 50% of the rainfall in this area is very less than 5 millimeters of rainfall. So that's the area where you have more forest atmosphere interactions. That's where the area where forests play a stronger role in forming rainfall. And that's the area that if you change vegetation, then probably the savanna will be very permanent there, because savannas interact in a different way. They do not evapotranspire during the dry season. So long explanation. So now let me just move more quickly to show the risks from these four drivers. Elevated CO2. CO2 concentrations are increasing. Of course, plants in general, they feel happier with elevated CO2, not too much. But water efficiency of plants, they fix the same amount of organic material using less water. Also, and of course, global warming, deforestation, forest fires. We are 1.1 degrees warmer in the Amazon, a little bit more in parts of the Amazon. Projections of IPCC 3 to 4 degrees. Total forest area in the Brazilian Amazon it's more than 780, about 1 million square kilometers in all of the Amazon. Forest fires also increased considerably. Let me quickly show you, and I also call your attention. Undisturbed forests, there's a lot of results in these inventories, forest inventories in the Amazon, and basically they show the Amazon is a very important sink. In a few years, 10 years ago, there was extracting up to 1 billion tons of carbon, the most important sink, but it seems, this data seems this sink may be reduced. This is a very troublesome data. If this sink shows reductions, it means the tropical forests, or particularly in the Amazon, may not be working as a sink for a long time. I just want to highlight a very important experiment that many people are planning for the Amazon, led by INPA in Manaus, but it's international. There are many US scientists, European scientists, Latin American scientists involved. This is an experiment of raising CO2 levels in a site 100 kilometers north of Manaus, and try to understand how the forest responds to that. I think, I don't know how many of you are aware of that. This is an experiment that's worth following and supporting. This is, and of course I did not show the results, but it increases resilience. If you increase CO2, let's say up to 450, up to 650, you have increased resilience. Of course, deforestation is an important one. I want to give you this data. Is also from a study, a former student of mine, Sampaio. So you basically, there are many of such experiments. You do deforestation up from 20% to 100%. But I want to illustrate why we came up with this 40% figure in the literature. If you look at this curve, it's exponential, and this is the rainfall change in that area marked in red that I mentioned to you. This is the most sensitive area for deforestation, for change in vegetation, for savannization. And up to 40%, there is a small change in rain. And then after 40%, it's more exponential. So that's slightly arbitrary, but that's why we came up that this is one of the tipping points, 40% of deforestation. And then you see here in the bottom, the resulting vegetation, the forest remains only in the western portion after you pass 40%. So this is one of the tipping points. Of course, fire is another one. Unfortunately, as I mentioned, fire is still very much used every year, and we are not making much progress. Hundreds of thousands of hotspots, of most are not forest fires. Perhaps 15% of them are forest fires, but they are really doing reducing tremendously the resilience of tropical forests. There's a lot of studies, and Anya Alenkar is here. She's she's one of the top experts in this type of study, and they are calculating this 3 to 10-fold increasing in vulnerability in forest fire frequency. Next, of course, is global warming. Global warming, depending on IPCC scenario, between 2 and 4, 5, 6 degrees in the Amazon. So there has been a number of studies. I'm just showing one here with IPCC models showing tendency to replacement for savannas. I don't have much time, but this is the worst case scenario. This is IPCC-RCP 8.5. I just want to show you why, unfortunately my time is running out, why you have more rain in the tropical, intertropical convergence zones, both in the Pacific and the Atlantic. You see those dark blue and green, and all this air rising there sinks in the Amazon. That's the reason why the Amazon will become drier, except the Western Amazon. So this is very important. So when you say 4 degrees warming is the tipping point for the Amazon, it's not the temperature. It's the hydrological change associated with that. So we made all these calculations and summing it up. I just want to highlight for all these scenarios, which is elevated CO2, we put more CO2, fire, which reduces vulnerability, reduces resilience, deforestation, and the scenarios of IPCC climate change, global warming. So just looking at the one with the circle, so basically it will tell you by 2050, with 20% deforestation, if we stop deforestation at current level, we are going to end up with between 50 and 40% of forest remaining. So this is, and if you continue with more deforestation, then it ends up between about 30%. So this is an integrated result showing, and this is the spatial. You see here the spatial, the forest will be in the left, a little bit of seasonal forest. So all of that made the Amazon becoming one of the tipping elements of their system, and this tipping element, along with all the others, I highlighted there, it's about 4 degrees, but it's not, as I say, 4 degrees temperature is the whole thing. And of course, in this graph here, global deforestation is not there. So basically, just to finalize, let me just very rapidly to tell you the risks. We are about 1.1. We are very far from 4. We are deforestation 20%. But what fire lengthening of the dry season and increased streams? We unfortunately are seeing, the explanation is not yet very clear, we are seeing a lengthening of the dry season in this area marked there by 6.5 days per decade. So this is very troublesome. We're still trying to understand whether this is related to local changes like deforestation or global changes in the Pacific and Atlantic sea surface temperatures, but still these observed. Fire, there has been a number of fires, this carried out by PIPA researchers, northern Mato Grosso, and this is very clear. Fires increase tree mortality tremendously. This is well known, very well known, and now we have quantification of that. And you see this progressive degradation of the forest, which is continuing. There may be between 600,000 and 1 million square kilometers in some level of degradation in Brazil and Amazon. And also something more mysteriously, which is the oscillation between climate extremes. We are seeing the system oscillating, and unfortunately, in a complex nonlinear system, when the system starts oscillating very rapidly, it may be a precursor of abrupt change, of a tipping point being transgressed. We have 3 events of drought and 3 events of wet periods, abundant rainfall in the course of 12 years. So this is, we still don't understand the dynamics, because it's not something like, warmer SST in the Caribbean, you have stronger hurricanes. We know the physics. But here, still the physics slightly mysterious. And so, conclusions, I just want to highlight my conclusions here. Basically, this tipping point analysis revealed 2 independent thresholds, which is the associated hydrological changes and temperature of 4 degrees warming in the Amazon, or regional deforestation exceeding 40%. Synergistic interaction among these drivers reduce considerably the safe operating space for maintaining the forest. So as Tom Lovejoy has been saying, and I agree totally with him, we should not move beyond 20%. Let's be on the safe operating space. The long dry seasons in 2005 and 10 droughts would be the norm if we continue with global warming. So the risk of the Amazon savannization is increasing substantially, and we have to pay attention to that risk. Amazon countries can reduce deforestation, but we have to act about global warming, which depends on Paris Agreement and depends on a lot of people, a lot of things, including this country going back to the Paris Agreement. I just want to finalize with this thing. We are doing these calculations now. This is the acai distribution in the Amazon, and we are calculating, I don't have the results to show you, but we are doing this calculation for 5 of these more acai, Brazil nuts, and several others. We are looking at what happens if we have climate change, for several scenarios of climate change. What is going to happen? I mean, is this commercially available? Like acai is the big hero in this new economy of the Amazon. Is this going to be the same? So we are looking at that now. We just want to see how climate change, global warming, and the regional deforestation might really put even this new economy at risk. And I finalize by just remarking my big hero for many years, Berta Becker, her famous sentence, to add value to the heart of the forest. We need science and technology to offer solutions for the emergence of innovative, knowledge-based, standing forest economy, and also development of local buying industry, along with empowerment and quality education for the forest people. And here, finally, my only religion, knowledge as the basis of sustainability for the Amazon. Thank you very much.